Okay, there we go. Okay, so this is going to be a fairly advanced talk about the usage and architecture of PGX. There's going to be a lot of code. There's over like 20 sample programs, and all the source is in the repo. I'll post a link to it on GitHub. It'll have the slides and all the sample programs that the sample code is drawn from. I'm assuming a fair amount of knowledge of Go, of Postgres, and at least some knowledge of PGX. So when we're talking about standard lib, we're going to assume knowledge of PGX interfaces even before we've actually gotten that far down, because part of what we're going to be talking about is how you go from one layer to the other. And our goal is that everybody gets something that you can use out of this. So to start off with here, we are actually going to start in psql here. All right. Okay, so we are just looking at psql here, and I'm going to establish a connection here. Whoa. Well, that was kind of weird, right? So I don't know if any of you are old school enough Unix hackers to be familiar with the fortune command, which used to show just some random code of the day when you log in. And if you're familiar with cow say, or it looks like I might have it configured to elephant say in this case. But we have seriously hijacked psql and Postgres here. So whatever we send it, like notice this isn't even valid SQL. We get something arbitrary back. So we are going to start out with the standard lib and database SQL, and we're going to end up going all the way down to the bottom of messing around really low-level Postgres stuff. Because PGX is a database driver and toolkit, and there's a lot of pieces you can take out of it to use to do other things, like this crazy psql pgfortune example. Okay, so with that as the intro to where we're going, the PGX is basically a stack. It has at the very top, it has the standard lib, which is database SQL compatibility. At the bottom, it has pgproto 3, which is the wire protocol encoding and decoding for the Postgres version 3 protocol. And here we go. So this is just a basic connection thing for the standard lib using database SQL. I assume pretty much everybody has seen something like this before, so we're not going to dwell on it. But here's just an example that we're going to start with. Where we get into a little more interesting is the driver passes through any query params directly to the underlying PGX connection. So what this means is when you're using database SQL, you can use the whole the PGX type system. So for example here, we are inserting an array, and we don't have to implement the database SQL, scanner or valuer interfaces. It just works. And that'll work for the native types that PGX supports. It'll work for the complicated types like box or circle or HStore, that type stuff. You can also use PGX types as scan targets. Now this is a little trickier. It requires using an adapter, and that adapter is this m.SQL scanner thing. Unfortunately, with database SQL, we're limited by that SQL scanner interface. Internally, the Postgres wire protocol, it tells us what type of data it is, and it tells us if it's in the text or binary format. But we've lost all that by the time it gets to us here because database SQL basically strips it all out. So we can use this SQL scanner thing as an adapter, and it'll work most of the time, but a few types will not work. Like, for example, one of the things that PGX does is you can use a map string to any, and you can just directly use that with JSON, JSONB, or HStore. Now, the wire protocol representations, the format of those values are entirely different. But because PGX knows what the underlying Postgres type is, it's able to figure out the proper mapping. With database SQL, it can't. So there's some cases where it won't work. And in addition, things like the generic types like array of T, it's lost the step there. But you can do a lot. Another place you can reach down a level is with custom connection configs. So you can use just a normal PGX parse config, and you can do whatever you want here. You pass that to stdlib OpenDB, and you get a database SQL database out the other end. But all your configuration that can't be put through a connection string, you can still do. So like, for example, here we have a onNotice handler. Now, notice is different. Confusingly, notice is different from the Postgres listen notify. So notice you get when you do things like drop table if exists when the table doesn't exist. You get some sort of message like this. So you can install hooks, before and after filters, things like that, custom TLS configs, custom dialers, custom DNS lookup, all those things that obviously don't fit in a connection string. You can still use it with stdlib by using a parse config and OpenDB. If, for example, you're using, I think it was SQLX was like this, at least back in the day, where you had to pass it the name of the driver and you couldn't use OpenDB directly. The stdlib also has this register conn config, which lets you basically smuggle a connection config into a connection string, which then, the third-party library can access. But it gets more interesting when we want to use like lower level PGX or Postgres functionality. For example, things like the copy protocol. That just isn't available with database SQL. Database SQL is the least common denominator of database interface. Well, there is a means, a combination of support with database SQL and with PGX, where you can get the underlying pgxconn, do whatever you need to do with it, and then release it when you're done. It just uses a callback function style there. So that lets you do things like copy. It lets you do things like listen, notify. Well, basically anything you want to do with PGX, you can get a raw PGX connection through this. So one of the interesting things about the stdlib is there's nothing actually special about it, as in it doesn't have any special access to the other packages. It's built on PGX and pgtype, but it's only 600 lines of code. So if for some reason you had some need to use database SQL, but the stdlib adapter didn't work for you, it's not actually that much code. You can just replace it, make your own, and you don't have to build the entire database driver layer. You just build that little interface between PGX and database SQL. Now, I don't think most people would need to do that, but it's designed so that type thing is possible. It's trying to be extremely modular. So next down the stack, or I guess kind of side by side with stdlib, is pgxpool. So if you're going to use the native PGX Postgres interface, you're probably going to need a connection pool. So that's what pgxpool provides. And the interface is very, very similar to just using PGX directly. In fact, it's almost transparent. It's just a concurrency safe. So the core logic is provided by this other library I wrote called Puddle, because it's a very small pool. And what that does for us is it lets the really nasty hard parts be encapsulated in another library. So one thing I've definitely learned in working on this is even in Go, Go is supposed to make concurrency easy. It might be better to say it makes it easier, but it's still really, really hard. So Puddle tries to encapsulate those hard parts so we can just focus on what's specific about a connection pool versus just a generic tiny resource pool. So the resource pool Puddle handles the complicated stuff of the concurrency. Then on top of that, we add some PGX specific features. So we add connection lifecycle callbacks, we add pool size control and health check type things. How long should the connection be idle before we close it? Do we always want to have minimum number of connections? All that sort of stuff. You can use the lifecycle callbacks to do some sort of monitoring or tracing type stuff. After connect can be interesting if you're using prepared statements. You can just make sure all of your connections have the statements prepared ahead of time. You can do setup for things like row level security, various, whatever you need to do on connect, you can do it. It also has a bunch of statistics it provides, how many times have things been acquired, how often did it try to acquire but have to wait. Again, it can be interesting if you're trying to diagnose or trace and monitor performance. So just like the standard lib, PGX tries to offer some escape hatches. So pgxpool has its own conn type, which it needs to allow you to release the conn when you're done. But sometimes you actually need a real pgxconn to pass into like another library or another function. So it does provide access to the underlying conn. It also provides a hijack method that you can use to take a connection out of the pool permanently. This can be useful, especially for things like listen notify, where you have a pool for your main application to handle, say web requests, but you also need one connection that'll listen for notifications, and you want to just grab that, from the pool directly, but then not have it be occupying space. So just like standard lib again, pgxpool doesn't have any special privileges. It's built directly on the PGX package. It can't access internals. It's only about 800 lines of code. Again, the really hard stuff is in Puddle. There's a very high bar for proposed changes, either to Puddle or pgxpool. It's been a lot of work to get it reliable and solid. And basically, we'd like to avoid rocking the boat on that because it is such a sensitive part. So no changes are planned, and any proposed changes are going to have to meet a really high bar. So the next one down the stack is the PGX package itself. So this is the main interface. And you can see with this example main function here, it looks pretty much like pgxpool. It's just we're getting back a connection instead of a connection pool. So PGX is very connection oriented. And that's important. That was one thing that I purposely did differently from the database SQL style, because for things like prepared statements, for things like listen notify, sometimes you really need a specific connection. And that abstraction of always working through a connection pool just felt like the wrong abstraction to me. I prefer to have the connection be the primary interface, which then you layer a pool on, instead of having the pool be the primary interface and then you have to dig down somehow to get an actual connection. So the basic interface mimics database SQL, query, query row, exec, except we've added context by default, since we're able to do major version releases and the Go language isn't. We're able to clear out that messy query context, query row context. We can avoid that. So this is just a standard query in the style of database SQL. And it is very verbose and error prone. I really don't like this interface, but it seemed appropriate to mimic database SQL as much as possible to make it easy for people to use. But there are a number of foot guns and error prone things. Excuse me. So the first one is a lot of people think, oh, I just checked the error here for the query. There was no error, so it must have been fine. But that's not true. The error is, hey, we successfully sent it or not. But it's entirely possible that the query will be successfully sent and then an error will occur later. In fact, it's even possible that we're going to get several rows in and then there's still going to be an error. Where I frequently have run into this is with divide by zero errors. So you have a query that has a division in it. You know, you're expecting 100 rows to come back. 10 rows get returned. The 11th row has divide by zero error. If you don't remember to check rows error at the end, you think, oh, I just got 10 error, or I just got 10 rows, and you never even see the error. So we frequently have issues posted on the issue tracker where, I had an error and the error didn't show up, and they're forgetting to check rows.error. So this is a really not great interface. You actually have 3 different places to check errors. The last one in particular is very easy to forget. So I really dislike that interface. What we prefer instead is the CollectRows function. So CollectRows is a generic function that takes a generic function of row to func, and we pass in a function that returns the value that's going to be accumulated for that row and an error if something went wrong. So the implementation here, what we write is pretty simple, and what we end up with at the end is a slice of integers. I know that generics were a little controversial in Go, but they are hugely valuable with PGX. So my vote is they were great. And if they want to add more, go for it. So one other thing to notice, by convention, when we use this style, we do not even bother with looking at the error from query, because any errors from query will be included in rows, and then they'll get passed back from CollectRows. So this is more of a traditional, idiomatic usage. Now, how do CollectRows work? So this is actually the source code for that generic function. As you notice, there's not actually that much to it. And the generics just work beautiful here. You'll notice that it's very similar to what we were doing manually. We have a slice, we go through each row, we append to the slice, we check the error, and we return. So it's a really nice, generics just made this, they literally just made it possible. Now, one extra thing here, notice this defer rows close. So this is another nicety about having a higher level interface than the database SQL style, is our previous example actually omitted that. And usually that's okay. But if a panic occurred, say while scanning or something, that would mean we could end up leaking that connection where we have the rows never being cleaned up. And if it's coming from the connection pool, that means we just leaked a connection entirely that'll never become available. Well, garbage collector might make it available eventually, but you can't rely on that. So this ended up being really convenient as well, because again, it's hard to use correctly the original database SQL style thing. So this is even better. Now we're using the generic row2 function. Instead of writing that 3 or 4 line function ourselves, we can directly use this. And again, it's a very simple generic function. It's only 3 lines in the body. And it lets us boil down to the entirety of us sending the query and collecting the results. It's only 2 lines, without the error checking. So that ends up being a much cleaner, much simpler interface. And we have a fair number of these type functions. They're fairly self-explanatory from their names. We can get maps, we can get the address of a thing, we can get structs, we can get, by position, by name. The only one that's not especially explanatory is the lax variant. So say you have a struct that has 3 fields and you do a query that returns 4 fields, or vice versa. Lax will allow that to happen. The non-lax version is strict and is going to throw an error. So here's an example for that struct mapping. Given this setup of, we have a temporary table here, we insert some rows. The code to select into a struct here is just these few lines. We can just use row to struct by position, and we end up with a slice of structs coming out the end. So I find that this was one of the biggest things with v5 of PGX that gave us a lot more convenience. So PGX util is actually where CollectRows first came into being. So it's kind of like my personal toy box of where I try new things. So I don't necessarily recommend you using it directly, but one of the next things on my list that I'm trying is a select function that wraps the entirety of the query and the collect into just a single statement. And I've been using it for, I don't know, maybe 6 months now or so, and it seems to work pretty good. So I wouldn't be surprised if this eventually ends up in PGX. There's another helper method here of for each row. So just like CollectRows simplifies collect to a slice, sometimes we want to iterate through the rows of a result. And this just gives us a simple, run this function for each row interface. It's not used near as often as CollectRows. Having to declare the scan targets outside is slightly awkward, but I wasn't able to find any better interface. And by doing that, it may avoid allocating on every iteration if there's some sort of complex scan target. So this is another one that's not immediately obvious that Postgres has, or that PGX has. And that is, when you're already in a transaction, you can call begin again. And you can see, we rolled back this inner one, and when we did the count of users, we only had 1. So if you know Postgres very well, you might realize, hey, Postgres doesn't have nested transactions. What's going on here? That's why they're pseudo-nested transactions. They're implemented with save points, or they're simulated with save points. And again, if you're a DBA, you're probably a little nervous about save points, and you probably should be. So before you actually use this aggressively in production, I would make sure to read these articles to make sure you know what the implications of save points are. But where I find them super useful is actually in testing. Oftentimes my application logic needs to be transactional, but then I want to run a test and I want the test to be a transaction as well. So you end up needing this nested concept. So by writing it in terms where a transaction can have a transaction, your test can start a transaction, pass that to your application logic, then your application logic starts another transaction, and it doesn't care whether it's a real transaction or it's one of these nested save point ones. So I found this not something so much that's super useful in production, but something that's super useful in tests, and useful in production if you're careful. Another helper method here is begin func. Just like query and then for next and then, rows.error, just like that pattern is very verbose and error prone. The transaction interface with begin can be fairly verbose and error prone. So begin func basically wraps the idea of if you return an error, roll back. If you don't return an error, commit. And it just kind of seamlessly wraps that stuff up so you have a lot less error checks to do. Whew. So I've been talking pretty fast here. Are there any questions or anything so far?
Have you looked how big is the performance impact on the trying to use this rows to struct by boss, for example?
I've not measured it extensively. There is a bit of overhead because internally it's going to use reflection. Even though it's generic, it uses generics to know what type of thing to return, but to actually do the value mapping to each column to field, it still has to use reflection. So it's definitely going to be slower than writing out the function by hand. In my usage, I have not found that to be a problem. But if you do, you can still use CollectRows. You just write out the function and manually scan, the different pieces. Cool. So now we're going to get down into the real details of how Postgres and any client program like psql or a driver like PGX, how they actually talk. So Postgres has two different execution protocols. It has a simple protocol, which is basically send a string over the wire and it'll send you back results. And that's it. Then there's the extended protocol, which separates out the idea of parse this SQL statement, bind some parameters to it, and execute the results. And then that supports parameterized queries. It also has the idea of multiple formats for a given value. So it supports encoding it into text, but it also supports a binary format, which is usually faster. PGX supports both protocols and both formats, and it prefers the extended protocol and binary when possible, but it's also smart enough to use the text format when it's actually faster. Initially, I was using binary format for everything, but a little bit of benchmarking found that text columns are actually faster transmitted in the text format. There's I don't think I'd say it was a bug, but there's a performance issue with how Postgres encodes binary values that actually makes it measurably and significantly slower to send text, JSON, those type textish columns over the wire in binary. It ends up doing I'm not sure the exact details of what exactly is going on there, but it's like 20, 30% slower if you ask for it in binary. So because PGX knows what the types of all the values are, it actually tries to ask for it in the most efficient form. As mentioned before, the extended protocol allows the client to know the types of parameters and of results. The problem is that entails 2 round trips. So you send 1 round trip to the database and say, hey, here's a SQL statement I want you to parse for me. And then it sends back, okay, here are the types of parameters I'm expecting, and here's the results that I'm going to give you, the types of results when you actually execute it. That's useful because you can ask it for stuff in the binary format. It's not useful because 2 network round trips is, that's doubling your potential latency there. So PGX tries to avoid that. It has has 5 different ways of executing stuff. So the first one, which is the default, is this cache statement mode. So internally, it actually is using prepared statements, and it maintains a cache. And after the first time it prepares a statement, then all the subsequent ones, it knows all the types, and it's only a single round trip. The next one is the describe mode. So in describe mode, it asks the server for the types, but it does not tell it to remember it as a prepared statement. So that can be useful when you're using something like pgbouncer, which does not support prepared statements. There is a risk though, and the risk is since you don't, since there's not actually a prepared statement, if somebody did a database migration underneath you, and for example, changed an integer to a float, you would still get a 4-byte or it would still be expecting a 4-byte value, but it could be interpreted entirely differently. So there's a little bit of risk of using this describe mode if you have concurrent database migrations. Then there's the exec mode, which just doesn't try and do any caching. Just every time you send a query, it does 2 round trips. Then there's another 2 modes where it does it in a single round trip, but the cost is it doesn't know what the types of parameters or results are. So exec uses the extended protocol, and simple protocol obviously uses simple protocol. But there are a few limitations as to how you encode parameters, because like that example we had at the beginning of map of string to any, that could be JSON or it could be HStore. There's no way for it to know how it should actually encode that. So those type encodings will either fail, or you can register Go types to specific Postgres types where it's like, okay, if you see map of string to any, assume this is JSON instead of assume this is HStore, for example. So speaking of network latency, that can be sometimes the biggest factor in performance. So PGX supports a batch query interface. You queue up however many statements you want, you send it, and either they all fail or they all succeed. So obviously we could have just used a single insert statement with multiple rows here, but for the sake of example, we did it as 2 inserts. One of the interesting things about batches is they use the extended protocol typically, and the extended protocol is implicitly transactional between the underlying sync statements or sync messages. So for this to be an atomic operation, you do not have to explicitly do begin and commit, because there's an implicit begin and commit wrapped around every batch. So sometimes you actually want to, do something with the results of your batch. So every queued statement can have a callback registered, and that callback will be run when you close the batch, or rather, as it iterates through there. So the convention or the idiom here is you queue up your queries, you add the callbacks, and then you just call send batch.close, and you check the error. And you'll get an error back here if any of your callbacks failed. There's another interface where you can just iterate over the results of send batch and handle the results there, but in most cases, the callbacks are much more convenient. So we mentioned this before, but batches are implicitly transactional. One edge case with batches is there is a limit to how many you can bundle together, but that limit is somewhat undefined and varies between network conditions, operating system, what have you. So there's a real risk, or there was, of actually just deadlocking entirely. If you have like several megabytes of queries you're sending, and you write those to the Postgres server starts receiving them, starts working on the queries, starts sending you results back, and it has several megabytes of results back before it finishes, processing those queries. It's possible both sides of the connection will deadlock because, your Go side is trying to write, and the Postgres side is trying to write, and neither of you is going to read. So all the network buffers fill up and you just get locked. So PGX handles that case now, where it'll spin up a background Go routine to watch for that case and buffer results if necessary. However, there are still some limits. So the implicit transactions in particular, there seems to be some sort of memory limit in Postgres. Users that have done like really large batches, or again, really large is kind of hard to define, have sometimes reported getting like Postgres sending them like an out of memory error of some sort. So 1,000 queries seems to be a good balance that you get good performance and you're not going to run into these issues. Because I mean, I've heard, some people may go up to like 50 or 100,000 and it'd be fine, but you're definitely getting diminishing returns when you go past, like 1,000 queries at a time. Hey, what's up?
So, one question about batch queries. Is there a way to do batched queries without the transaction? Or is it like hardwired into the Postgres protocol?
That's actually hardwired into the Postgres protocol.
Okay.
Yeah. So I say that. There actually is, if you really, really, really need that, we'll talk about at a much lower level, there's a way to get around it a little bit. But at the Postgres protocol level, you send these, you send the bind or the execute messages, and you also send sync messages that say, this is a sync point. Everything between the sync messages is transactional. So if you go down far enough where you actually choose which messages to send directly, you could create a network message that you would send that would include like exec query sync, exec query sync, exec query sync, and you could send all of that in a single network write. That would solve the latency issue, and that would separate the queries out. It's not real easy to do, but I guess technically that would be possible.
Good to know.
So just to cover a few other features of PGX that people might not know too much about. Most people probably are aware of CopyFrom, but what people might not know is just how fast it is and how quickly it gets faster than using insert. So in the documentation, I mentioned that it can be faster with as few as 5 rows. I've actually seen it faster with 2 rows, like literally a copy with 2 rows versus 2 inserts. So, I mean, that's kind of crazy. So anytime you need to insert multiple rows and you care about performance, you really want to look at CopyFrom. We also have a wait for notification as a convenient interface to the Postgres listen notify system. It buffers notifications internally. So that lets you use it for tools that have a single Postgres connection where you're not using a connection pool, where it's like, let me do some queries and work, then let me check and see if I got any notifications, and you kind of like bounce back and forth between those things. You can do that with wait for notification. We also have a bunch of tracing interfaces where you can put in logging, tracing. Some people have done some open telemetry integration. You can pretty much do whatever you want there. And we also support large objects, which are one of the really, really obscure parts of Postgres. Large objects are basically when you want Postgres to be your file system. So you open a large object and then you basically have like read, write, seek like into this file, basically. And then you get Postgres transactional semantics as well, which is kind of cool. But I don't know if using Postgres as your file system is a great idea, but you can. So recurring theme here, PGX is modular and built in layers. No privileges or escape hatches. or there's no special privileges, and there are escape hatches. So pgconn and pgtype are the underlying libraries here, and they're separate packages, so it doesn't get any, special access. There are escape hatches here where if you need to dig down into the underlying type mapping system, you can get that from pgxconn. And if you need to go down to the Postgres conn layer below PGX, the pgconn system, you also have access to that. It's not often you actually need to, but you can. So the next package here is pgtype. pgtype is what converts between Go and Postgres types. It's the largest PGX component, and it's pretty complicated. But it can do just about anything. So a few key concepts is the way Postgres tells types apart is there's just an object ID. So like if I recall correctly, the integer type is OID 23. And I've definitely been doing this too much if I remember that. pgtype has a map type that is primarily responsible for encoding these things and decoding. A codec actually does the work, or it plans how to do the work for a given OID. And a codec gives us back an encode plan or a scan plan. And codecs usually have a pretty simple interface for easy extension. So let's look at an example here of a built-in type. So let's say we wanted to use Postgres circles, and we didn't want to use float 64s. So internally it's a float 64, but we really wanted to use float 32 just to save space on the Go side. Well, pretty much every codec exposes a set of scan and value interfaces that you can implement here. So you notice this scan circle and this circle value. One gets a pg-type circle, the other returns a pg-type circle. What this allows is it allows you to integrate Postgres types into your types without actually having to write any parsing code, whether for like the text or binary format or any formatting code. So it's really convenient to be able to be able to use your application types directly in PGX. And here's the example of how it's used. Again, you can use it directly since it implements those interfaces. And you don't have to worry about text or binary format or anything like that. So codecs are what actually handle any specific Postgres OID. And you can register new ones. You can replace all the existing ones. So if you wanted to change integer type to do everything in Roman numerals is how it would scan stuff, you totally can. Now, why you would want to, of course, you wouldn't, but it's entirely pluggable. You can just override everything. But it is fairly complicated because you need to handle encoding binary, encoding text, and scanning binary, scanning text. You end up with these interfaces like that circle scanner and circle valuer. And I mean, to give you an idea, circle is about as trivial as a Postgres type as you're going to find. And it's just the codec there is like 200 lines of code. So you can do it, but it's a fair amount of work. And if the package docs talk some about it, you'd also want to actually look at the circle codec or a similar simple one to get an idea. I mentioned plans before. So a plan system is really important for things like this. Wouldn't it be nice if we had a type, for example, a tag that's a special type of string, and we didn't have to implement scan, value, whatever type, stuff like that, if it would just work? And especially then like, oh, well, we have our custom type of tag. How about a slice of tags? Can I just scan that from an array of strings? And in PGX, you can. And the key behind it is plans. So we mentioned before that codec doesn't actually do the encoding directly or decoding. It actually provides a plan for how to do it. Well, the way pgtype actually works is it looks up the OID and it asks the codec, hey, do you know what to do with this Go value? If it doesn't, then it tries all these different wrapping things. So it'll recursively go through here and say, hey, I don't know what to do with this thing. Maybe it's a pointer to a pointer. Or maybe it's some sort of built-in type like net.ip, where we do know how to handle the Postgres equivalent to it, but we don't have the ability to add our own interfaces on top of it. So maybe it's something like that. Or maybe it's a structure, or maybe it's a pointer to a struct. All these different things. It tries to go through them. And if it finds a match, it creates a plan that wraps the underlying codec plan. This allows a codec to support many types without the codec actually knowing about them. So in our example of the slice of tag, well, it goes through that thing and it says, oh, this is a slice. So let me try wrapping it in a plan that deals with slices. And it says, oh, but I don't know what tag is. So then it says, well, let me try and unwrap this type and find out what the base type is. And if it's a type that I know of, then I'm going to treat it, as that underlying string. And you end up with it recursively looks through all these possibilities and builds the plan, that can unwrap the type and figure out what to do with it. This can be slow, though, because it's got to try a whole bunch of possibilities. So plans are cached. That's part of the reason why a codec does not directly do something. It's because we want to be able to cache the plan that has all these wrapping things. It also lets us seamlessly add support for types that we can't change. So like a decimal type, a UUID type, even in the standard lib, something like time duration. There are these try wrap functions, look for them and say, hey, is this a shop spring decimal? Well, if it is, let me wrap it in a type that implements the PGX types and then unwraps it on the way out. So that lets you end up using like a PGX decimal or the shop spring decimal type directly without having to manually wrap stuff. That's a big win for convenience. pgtype also supports array and composite stuff in a really interesting manner. So given this setup here, we've got a table of teams, we've got a table of players. One other thing here, notice that we are passing multiple statements to a single exec. Because there are no arguments, exec knows, oh, I'm just going to send this over the simple protocol, and the simple protocol can have multiple statements in a single string. The extended protocol cannot. So that's why this works. So wouldn't it be nice if this actually just worked? We have our struct of team. It has a slice of pointer to player. And we just run this SQL query, which is going to have a nested subselect. It gets us an array of the players for each team. That would be really convenient if that just worked. And it does. So this is a really interesting way of loading object graphs. Traditionally, you would maybe use an ORM, and like if you've used Rails, being able to preload stuff, that's a common way of doing it. But this is perchance even a little simpler because you just directly write the SQL to say, give me the object graph I want, and it'll, scan it into all the pieces you care about. It's potentially better performance as well, since it's literally just a single query. An alternative is to use batching and to manually do that stuff. That's possible. This is usually a little simpler. There are a few limitations with this. You typically need to use the extended protocol and the binary format. That is because the text format just gives you like parentheses and then like comma separated values, but it doesn't tell you what type it is. The binary format for the record row type actually includes the OIDs of each component, so we're actually able to know what to do with it. Depending on the type of row or the type of struct, if it's a named type, you may need to register it with PGX. There are some helper methods for that. If you need to load a type from the introspect the Postgres catalog and then register that type, there are helper functions in PGX that handle that. This register default pgtype, that was what I referenced before about if you're using the simple protocol where you don't know, where PGX won't know the remote type. This is how you say this type is always going to be JSON, or it's always going to be HStore or something like that. Another interesting things here, again, the idea of modularity and layering. pgtype doesn't actually know anything about like Postgres or a connection. All it works with is byte slices, OIDs, and Go values. So that one thing that makes it pretty easy to test, but it also can be useful if you want to pull this logic somewhere else. All right, we're getting down toward the bottom of the layers here. So below PGX is pgconn. So if you've done some C programming with Postgres, you may have run into the C library libpq. That's the core, provided by the Postgres project. That is how they support talking to Postgres. It's low level and does not do any type conversions. You're rarely going to use it directly, but there are some things that you can only do here. So it's kind of some cool stuff. If you really need to get everything you can out of Postgres, this is one of the places you can do it. So connecting is basically the same as it is in PGX, the higher layers. And that's because the higher layers are just delegating most of the stuff down to the pgconn layer. What's a little different here is since I wasn't bound by trying to match database SQL, I was able to correct the interface of returning rows and an error. Instead, we return a result reader, and the result reader gives you an error at the end. So I was able to actually clean that up a little bit. Exec uses the simple protocol, so we can pass multiple queries at a time. The MRR is actually because we get a multi-result reader. So we loop through the result sets, and for each result set, we read through each row, and then we print out the results. If we use the extended protocol, we directly specify that. Now this gets kind of verbose. So the extended protocol does directly separate parameters from SQL text. So like internally, that's what PGX uses whenever it can, and that's like really important. So we can see here we pass it the SQL text, then we have to pass it the param values. Then we can tell it exactly what OID, and we can tell it exactly how the params are formatted, and we can directly tell it how the results are formatted. Now, obviously, this is a little more verbose than you probably want to do on every query, but we can see what comes out here. We're actually just working with byte slices. So the results, the first result is going to be 1, 2, 3. We can see the literal bytes we got formatted as a string, 1, 2, 3. Then the next one here is a float formatted as a string. So we see the 1.1, 1.2. And then, whoa, what happened here? Well, imprecision of floats, we ended up with this crazy text representation. And then finally, we can see that for the last one that we told to represent as binary, well, we just got, raw bytes back. And we have to, figure out what to do with that. So we're usually not going to to use this directly, but it is available, and it's what PGX is built on. PGX calls this stuff internally when you're executing queries. Where you might use it, and this actually is the answer to the question earlier about can we control the atomicity or implicit transactions. This is actually how. So pgconn supports a pipeline mode. It's extremely verbose, but it's how you can do that type thing. So we start by starting a pipeline. We queue up some queries, and all these nils are the same type thing we had with the example before, where it's like what type of parameter, the OIDs of all that sort of stuff. And then sync says, hey, actually send this thing. So we can control exactly when something is sent over the wire. Now, this actually did the sending. All of this code is just to read the results of the first query we sent. So like I said, super verbose. So results is basically reading more or less a single message off the wire. If it recognizes it as a result set, it'll give us a result reader. If it recognizes it as something else, it might be something, like a sync, for example. But we have to read the results, make sure what type of result we got. Then we actually read the results normally. And then we do it again for the next query. And then we do it again for the next query again. And then we have to read that, hey, that when we sent that sync before, Postgres will tell us, hey, this is a sync point. So, and this is also why we have to do the type assertion here, because get results can return multiple types. And then we can send more queries and then sync them. And I will omit the rest of actually going through all those reading things, but you can kind of see extremely verbose, but you can control down about as far as is possible in Postgres. You can control exactly how things go over the wire, the exact bundling of these implicit transactions. You can also prepare and deallocate statements. I didn't show an example here because I already figured I was going to run out of time here. This is what's used to implement PGX batching, or it's one of the strategies. And it's pretty clever. So say that you're going to batch 100 queries. And of those 100 queries, there's actually 10 different query texts. And, it's 100 different parameters you're sending. Well, what PGX will do is it'll do one round trip where it says, hey, prepare these 10 different queries. And it'll make prepared statements for all of them. Then with the next round trip, it'll say, now execute all 100 of these at once. So it's pretty intelligent about using the pipeline to minimize round trips as much as possible while still using the extended protocol. But like we said, very, very verbose, almost at the level of individual protocol levels. And it requires a good amount of understanding of the Postgres protocol. For something low level, or for something that's at this level but is also really useful and doesn't require you to be quite so crazy down into the Postgres details, is CopyFrom and CopyTo. So PGX has a nice layer on it where it handles encoding all the types and whatnot. pgconn doesn't. But what pgconn does do is it gives you a reader and writer interfaces for just that direct byte stream that is going to or from Postgres. So this is an example adapted from one of my actual projects where I need to copy data from one Postgres server to another. Well, in my source server, I call CopyTo, and I just tell it, do whatever query is going to give me the copy data. And I say that should be written to an IO writer, which is one half of this pipe. Then in my destination server connection, I say copy from, and I pass it the read end of that pipe. And these few simple lines can just directly copy data, from one server to another. So it's a really fast way of bulk data transfer. It can be pretty useful. The copy protocol supports binary, it supports text, it supports CSV. pgconn doesn't know anything about that. You're responsible for formatting it. But for things like server to server, that's pretty trivial. So pgconn has a few escape hatches. Front end allows access to the underlying PG protocol layer. There's a receive message method, which directly says, hey, I just want to read the next message. Conn lets you get the underlying net connection. So if for some reason you want to directly write bytes to the server, you can. And hijack lets you grab all the internal state and the net conn and just takes it over. That, again, is a very rare thing you would actually need to do. But what's interesting about it is, let's say you wanted to make your own Postgres driver. And you thought PGX's abstractions were wrong, you wanted to do something else. Well, you could use pgconn to set up the connection to Postgres, handle all the crazy stuff with TLS and authentication and scram and all the different ways of authenticating and setting up the connection. You could use pgconn to establish the connection, then hijack the net.conn and do whatever you want. So again, this idea of being modular and a layered approach. All right, just about done here. So pgproto 3, this is the bottom. This is as far down as we're going. So pgproto 3 is a library that handles the actual wire protocol. Your typical program should never need to touch this. But if you want to build your own load balancer or proxy or some sort of other middleware, this can be your friend. For an application, there's one place where you would use it, and that is that it supports debug tracing. This is similar to what libpq does. In fact, it tries to mimic it as closely as possible. You turn on tracing, and then you just do whatever you're going to do. The trace, you tell it a writer to write to. So when we run this, this is what actually gets printed out. The F is for front end, the B is for back end. That says who sent the message. The next thing here is exactly what Postgres message was sent. The next thing is the size of the message. And then there's some representation of that message. For the query, it'll actually be the string. For some of this stuff, it's a little bit harder to read. But this lets us view, without using something like Wireshark, what actually is happening over the wire. So you can see here, like, this was a simple protocol thing. So the entirety of the query was just sending a query message. For our next example here, we're using exec params, and that's the extended protocol. And we can see that here we're actually sending, a parse, bind, describe, execute, sync. We're sending all of these messages. And then we get all this stuff back, and we can see, oh, well, there's some stuff here that is obvious. This is the text format. And then there's some stuff here that is, binary formatted stuff. So it's useful for debugging and developing PGX itself, but it also can be useful sometimes if you're, again, working, like, especially maybe with the pipeline mode or something where you need to confirm exactly what's happening over the wire. And this will tell you. Okay, so back to the beginning. This is how that worked. pgproto 3, there is an example in the PGX repo. It's under pgproto3/example/pgfortune. And it builds a fake Postgres server that whenever you send it a query, it responds with fortune piped into Cause. And it's a couple hundred lines of code. So I've already run way over time here, so I'm not going to look at the code. But it's fairly understandable, and that gives you a head start on if you wanted to build like a Postgres proxy or middleware, or if you just wanted to make your own database that speaks Postgres, it kind of gives you an idea of how that stuff works. And that's it. All the slides, all the example programs, all 21 of them are on GitHub at that address.